Yes, part two. Yes, that's what it is. Of this response video to this video. You know, it's not a response so much as it is just a way of, look, this is what, you know, this is how somebody else presents science, and I'm just saying, okay, well, this is my opportunity to just interject. This is where I think they have it wrong. That's about all you can do, right? And see. You know, I really should just make comments on people's videos and try to drum up a little interest that way, but I just find that tedious because you really can't say what you need to say in comment sections. You know, it's just not sufficient to make an argument that way, for me personally. But anyway, so let's continue.
Mechanics needed to take into account electrical effects on the masses involved. This is a pivotal idea for gravity.
Alright, so he's arguing that there's something about gravity that cares about the condition of the matter. And my only argument would be is that a full battery, you know, a battery that's charged, has a different gravity, capacity to block gravity. So again, when we say gravity, you know, it's, you know, this is where there's a perspective problem. Because, yeah, we see gravity as something that something has, and it's something that happens to something. So that's the, you know, it's a disconnect in the language where it's a little bit broken, and it just does create a problem in a couple of places where you say, I've said things that I didn't mean to imply, because I'm saying it has gravity when, no, it doesn't have the gravity. The Earth is blocking the gravity can't get to the moon, blah, 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 that kind of thing. And so gravity is what happens to something. It's not something generated by something. So the internal electric effects, you know, how much is binding, how the matter is bound, is relevant to its atomic weight. I mean, that's sort of relevant to what something is. But that atomic weight, we know, changes subtly through chemical bonds. And that's, again, a full battery has more potential to block gravity. It has more mass, as we define it, because it has more of this quanta in it. It has more little bits that are interacting with the gravity bits. Yeah, that's about as plain as I can put it. So it's quite irrelevant in a way. It's not pivotal to understanding gravity. Is to understand the charge, to understand the gravity binding the internal atoms together. To understand what's happening to bound objects, it doesn't do you much good to understand what's binding the interior of the bound object. It obviously has to be, it's represented by its mass. It already shows, it reveals itself. It doesn't, there's no hidden mass.
Understanding gravity is essential to be able to express mass in terms of weight in kilograms. So here was a guy, another one, who was well on the way. Once again, good physics needs to be simple.
Says you, good physics needs to be simple, is what he just said. Yeah, I don't know about that. I don't know whether that's necessarily true. But what I think it has to, good physics has to be accurate. That's the real problem. You make a mistake somewhere in the ladder, you miss a rung or two. The truth is you fell down and you just don't know it. You know, if you've got the rungs wrong, you never climb the real ladder. You're just climbing, you're on the ground with a broken leg, and you're pretending you're still climbing the ladder, but you're not really climbing the ladder because you fell off the ladder. So it's really important to get the foundations right. So good physics is accurate physics. yeah, I think it's a better cliche to live by.
So Oliver wrote, it may be that when the structure of an electron, remember at present it has no structure. Once it's understood, we shall see that an even-powered stress in the surrounding ether is necessarily involved.
There you go. That's just so, you know, bang, there. And people got that. An evenly distributed pressure is what's holding these things together. And that pressure is gravity. And the reason why gravity we don't realize it as a strong force that it is because, yeah, it's really, it's personal, on the electron level. The things hitting it are big, and it's a very powerful force. So they call it mathematically insignificant because they don't realize that the strong and weak forces are made out of it. That's the manifestation of gravity.
What I do feel instinctively...
I mean, again, it's the manifestation of gravity polarized. It's what you get out of gravity. Gravity is magnetism. All these things are gravity. They're just manifested differently because it's polarized gravity.
Is that this is the direction for discovery, and what is needed is something internal and intrinsic, and that all attempts to explain gravitation is due to the action of some external agency, whether flying particles or impinging waves or Higgs bosons, he could have said, are doomed to failure.
Well, there you go. But see, now he just said exactly the opposite. So here we say, we shall see that an even-powered stress in the surrounding ether is necessarily involved. Right there, he just said, well, what's causing that even-powered stress in the surrounding ether? Well, if you just make the ether made out of this kinetic energy, out of these kinetic bits, and you recognize that they're kinetic, therefore they don't dispense heat. They don't even know what a friction is. They have no idea what any of that crap is. Then you understand that that's causing the pressure. The ultra-mundane particle, for fuck's sake. But here he's saying exactly the opposite and saying, well, I'm negating the creation of any kind of particle that creates the pressure. Well, you're negating it based on what reasoning? Probably the same wrong reasoning of the past, where people presumed particles to be solid objects, electrons to be a thing, a planet, and that you're crashing meteors into it and breaking off little bits. Well, that's not what you're doing. The electron is made out of element, quanta, and quanta hit it. And quanta, not quanta. There's no subquanta. There's no double quanta.
He's probably spinning in his grave at the waste of the LHC experiment. He showed insight and uncommon sense with his idea that the electron must have structure. All subatomic particles must have a charged subparticle structure and orbital motion to have self-energy.
Well, see, so he's saying structure and orbital motion, again, denying the fact that, no, what they really have is that they're not made out of, they're not a thing, they're not a machine, they're not a solid thing. They're made out of this elemental thing, and the elemental thing is doing exactly what it's doing in the big universe, which is clumping. Yeah, it just clumps by different rules because the rule is that it's really engaged. It's quanta against quanta on the nuclear level, where on the big universe level, it's quanta against 10 zillion quanta. I mean, obviously, it's going to appear as if that's a weak force, a weak game, a weak fight.
Or mass, and exhibit magnetic polarization, which is called, confusingly, spin by particle physicists.
Yeah, well, whether you... Spin is, I think, rotation has a lot to do with how you create, how you orient quanta. So, I mean, how does a quanta get polarized? It likely has something to do with rotations or something else. But, I mean, whether you call it rotation or spin, I don't know if that's too important.
This is where language gets into the way of physics today as well. Now, if we're going to talk about particles and matter, we have to look at the scale of the atom to give you some idea of what we're talking about.
Okay, here we go. With the nucleus the size of a ping-pong ball, the electrons would be the size of a flea orbiting outside this 100,000-seat stadium. So, well, he says outside the stadium. I mean, you should just use the field. But let's just say, for the sake of it, ping-pong ball in the center, flea out here. Yeah, that's our representation of the standard model. But what I would argue is that what we know is that this thing, just one atom, could likely not only just blow up this house, but could blow up a significant part of the area surrounding me. One atom. has significant energy, has significant quanta in it. Disruptible, if you release it all at once, it will break a lot of other atoms. It will cause disruption in their function. Yeah, stuff will happen. You know, and so this is full of these little BBs here. So to argue that this is all empty space, we don't have any proof of that. And I would almost argue that the electron might just be an illusion of net, what we see as a net product. But the real product is that this whole thing could just be full of quanta, relationship quanta tied to each other through this bounding pressure. But regardless, it really doesn't, understanding exactly the mechanics of this interior isn't terribly vital. The vital part is just to get the idea that the reason why this has a function or shape is because of the fact that there is a pressure that's of the field that's imposing on it, and it itself has a configuration, a boundness between these objects, where they're like a magnet. They're bound in a condition, and you have to do a certain thing to knock them out of that condition. You have to expose them to a certain amount of energy to release that bond.
The first step then is to give some idea of scale.
Yeah, I don't know if we need to do this part, so I'm just going to skip ahead a little bit.
Here's another guy. You don't hear about these people. I think Newton said that if he'd seen far, it was because he'd stood on the shoulders of giants. I would suggest that you have to be very careful in your choice of giant, because he may be facing the wrong way.
Yeah, well, you know, this, I don't know. I don't know if it's a great metaphor for doing anything, is to embiggen contribution beyond the fact that you acknowledge it. You know, but I just don't know if there's any point in trying to say who was the giant and who was the midget. Yeah, I don't care for it.
The people who should be in our science education curriculum.
I suppose just cite the important discoveries and just say, okay, we just give credit where credit's due, so to speak. But I just don't know whether, you know, there's just nobody's perfect, so to speak. So if somebody gets one thing right, doesn't mean they got anything else right. You know, it's that kind of thing.
Lynn was a philosopher of science, a visionary logician, and dedicated theoretician. In 1930, Fritz London explained the weak attractive dipole electric bonding force between atoms, known as the van der Waals dispersion force, or it's named after him also. It's the London force, which causes gas molecules to condense and form liquids and solids. In other words, planets and you and I and everything in the visible universe.
But again, what's really pushing them together is gravity. It's just gravity enhanced by this idea of polarization, where if the stuff is coming at me this way because of my arrangement of my matter, it doesn't affect as many bits. But if it comes in this way, it affects, you know, twice as many. That kind of argument. And so if one part of the nucleus of an atom is sending out this, and one part is sending out this, at different turns in that atom, at one moment I'm going to be pushed towards it, the next moment I'll be pushed away from it. And the idea would be is that the one force is stronger than the other force, and so slowly but surely you get drawn in. Again, not drawn in, pushed in.
The London force originates in oscillating electric dipoles caused by slight distortion of otherwise electrically neutral atoms. So here we're talking about the kind of stuff that the Earth and the planets and the Sun know.
Yeah, but this is where this gets, this whole conversation gets kind of mushy, just because, you know, as soon as you start talking about dipoles and magnetism, well, we know that the Earth is magnetic, and that's very different than gravity. And very different, I don't mean by very different, it's made out of a different force. I just mean that it's another manifestation of gravity. but it's a very different manifestation, is that now it's sensitive. This polarization thing has become a relevant and meaningful element.
Are made up of. The tiny electric dipoles arise because the charges within the atom are separated, as shown in the last slide, by effectively a huge distance.
Right. And by charges, he means there's these negative electrons circling these fundamentally positive nucleus. And that wouldn't make sense. Yes, it would, but that's if we understood it as regular orbits, but they're not really regular orbits. So that's what screws the whole thing. What's really happening is the quanta keep hitting other quanta, and they're constantly changing direction, forward, back, up, down. And the preponderance of their condition is that they will be in one position more than they're in some other, going some other way. So overall, 30% more time is spent going one way. So they end up having an orbit, but it's not an orbit made out of any, what we would traditionally call consistent direction. It just ends up that way over time because of the fact that the field absorbs whatever you throw out. So whatever garbage leaves you, that's in the field now, and the field is what you're existing in essentially. And so like if all the atoms are throwing out plastic bottles, there's going to be plastic bottles coming into your yard.
The electric dipoles resonate, as I said, they sort of tune into each other and orbit in such a way that they combine. See,
I mean, this isn't, to me, very useful physics. They orbit in such a way, and then they combine, and they do blah, blah, blah. I don't even know whether it's really the point. I mean, using the word electric dipole is almost, I mean, it's just game language in a sense. The monopoles don't exist. in our reality. And so what you're really talking about is a condition where something has an excess of something and the other side has a lack of something. So again, we're back to this gravity argument where one end of you is sensitive to polarization this way, your butt, and your head is sensitive to polarization this way. And you're creating the exact opposite thing of sensitivity. So you're creating the thing your butt's sensitive to, and your butt's creating the thing your head's sensitive to, that kind of thing.
It's always attractive, just like gravity. So there's a clue.
Well, it's always attractive. Again, again, that's his argument that it's a pull force, not a push force. But he's going to revise that later.
So, in fact, Fritz London said that it seems that gravity may be this kind of interaction between neutral matter. So it seems that the clue about the real nature of gravity has been available to chemists who are not interested in gravity and unavailable to astrophysicists who are not concerned with physical chemistry or electricity. Obviously, gravity has the distinction of being much, much weaker than the force between atoms, the London force. But that should be a...
yeah, but that, to me, is just a canard, because the weakness is just an accusation of wrong perspective. You're not realizing that on the scale of the atom, the quanta is much larger, obviously. And so it's not a weak force.
Blue. We are bonded to the Earth by a similar but far weaker version of the London force between atoms. And here we get into the idea of repeated patterns in the electric universe.
Yeah, well, this whole, I mean, what they're arguing is that somehow there's a static electricity between us and the sun or something, and that's bonding us, and that's the gravity, and it's a shadow gravity, inverse square, and all that stuff.
So like gravity, the London force is always attractive and operates between electrically neutral atoms and molecules. Very much like that.
Well, again, electrically neutral doesn't make any sense. As soon as you make an atom, a dipole, and as soon as you have this proposition that there's elements of it are spinning, it loses this idea of pole. I mean, the pole is now spinning. So at any 1 minute facing you, it's a very different thing. So you're never electrically neutral. It's almost like calling alternating current electrically neutral. It's not. Okay, so, I mean, it's up and down, up and down. You know, so yeah, the net result is, as you could argue, is some nothing, but we obviously know it's not nothing. The up and down means something. And in both directions it means something. It's really up and up. It's just a mistake of words or language to assume that you can have something and call it a static thing that from all directions is neutral. If it's neutral in some direction, it's not neutral in some other direction.
Good. So we can talk about matter and mass. So the second step on the path to discovery about what gravity really is to look at the particles that make up matter. Newton's law multiplies the masses of two objects together, so the first requirement is to define what is meant by mass.
Well, let's you know, I just don't think that's that difficult. You just call it atomic weight. So you just add up these elements, and you say neutrons are usually neutrons, protons are usually protons, electrons are usually electrons. But the idea is that this atom, depending on its arrangement, can throw away one of these electrons, which is a lot of mass, or it can gain an electron, which is a lot of mass, and that there is this field that is always affecting it, and there's likely quarks and little bits that are playing a role inside of this atom in terms of strengthening or weakening these orbits. So yeah, there's a connection, but it's made out of a real thing. It's not made out of nothing, it's made out of something. And it contributes to the total mass of the atom. But obviously these things are very hard, you know, it's really hard to see these things inside this form. And that's why they smash these atoms, is to break all these little bits off and break the structure. But I mean, when you do that, it's like crashing a car. It's a little hard to construct what is a piece of something bigger or what was a piece in itself.
The electron is defined as a fundamental indivisible particle.
Well, obviously that's wrong, so we agree on that one. And I don't, you know, that definition I think is getting fudgier and fudgier, so I don't know what the preponderance of, if I asked a physicist, do you think an electron is divisible? I think they would argue, yes, it is divisible. It breaks into energy, radiation. It's made of stuff.
But it must be a composite of smaller orbiting charged particles, shown here in blue, to store energy.
Exactly. So I think, like I said, these two statements I think are correct. I mean, I just think that this idea that it's a fundamental indivisible particle, I think that's old physics. I mean, I think everybody kind of agrees that that's not a working description. It's a machine, and the argument is whether it's the simple machine just made out of quanta or whether it's some other kind of machine.
The energy is stored by the motion of those charged particles with respect to one another, and also with respect to all other particles in the universe.
So again, he would say it's stored in something called momentum, and you know, my argument is none of these things have anything called momentum. There's no momentum in any of this stuff. What it is little bits that are still moving the speed of light, in the sense that there's a position, okay, that will always be, you know, that'll tend to be predominantly in one direction. So each position maintains this idea of an orbit, but frankly each thing is not moving in an orbit. It doesn't have momentum. It can as easily go left as it can go right. It can go immediately from going left to going right to going left to going right to going right twice to going up to going down. It can do every direction all the time, any direction, anytime, and there's no kinetic friction whatsoever because it has no momentum. It's a thing going the speed of light, and all it's happening is it's changing its direction because it has interaction with other quanta that are going some other direction, and so that place in space changes its orientation. That's all that's happening. These are places in space, and these places in space change their identity constantly. But the predominance of the time, their probabilistic, okay, circumstance is going to be consistent with this one always going this way. Like 30% of the time it's going to be going this way, and this one will go 30% of the time this way, and this position 30 times that, and so that'll be its consistent net byproduct is going to be, its overall effect is going to be this shape. But doing this shape, it did all kinds of wacky packy stuff. But the net in all four dimensions, that's what it comes out as a net. But the sums that went into making that net, you know, all over the place.
The same goes for all subatomic particles. Doesn't matter what it is.
Right, neutrons, protons, electrons, they're all quanta, made of quanta, and the quanta are just little bits moving the speed of light. And everything's just fundamentally comes down to, in a sense, a position in space. And what is the orientation of that position in space?
Including the neutrino. The neutrino also is included.
Yeah, well, I don't know if a neutrino is really an anything. It's, you know, it's could essentially be some element in atoms that does this thing where it's just a secondary holder of position, where in that it transfers, you know, the magnetic condition is just amplified and reversed, and then to create a circumstance where there's a strong enough bond to keep the electron at that distance. But that's it. It's just a way of supplementing. It's a you know, I mean, they use the word gluon. I mean, a lot of these things are just gluons. I think they're just elements that exist to extend force carriers.
And there was a report that I got yesterday that they have now shown that the
Anyway, okay, so they've now shown, well, here, I'll listen to this.
neutrino has mass. Now, the very idea that it didn't have mass meant that it couldn't have been a real particle anyway.
Right, well, the very idea that photons don't have mass is silly. So, yes, they're quanta. Quanta are the element of mass. They're the one, and if we just start with that, okay, and then call an electron a million ones, and then move on scaling, you get the idea. But anyway, I gotta go to work, so till later and such. I have returned. Anyway, so I guess we'll just continue, see if it plays. Probably ad will play, blah, blah, blah. Let's see what happens.
Because there was no such thing as a particle with no mass. The problem then was that, according to the standard particle, or standard model of
standard model. Yeah, according to the standard model, yeah, okay, well, yeah, the standard model is just sort of made up, you know, mostly.
subatomic particles,
My computer really isn't that bad, but, you know, this is some of the things it does sometimes. I'm not asking that much from it.
The neutrino doesn't interact with the Higgs field, as it's called. That meant that there was something seriously wrong with the standard model. So what has happened?
Well, again, the Higgs field is a whole. That's you know that's in addition to the standard model that you know say is kind of unstandard. So that was invented because the standard model had no way to stay together because it was relying again on this notion of momentum, and momentum is different inside an atom. As you start quantizing and get closer to the quanta, momentum is a lost notion because everything then it just becomes movement at the speed of light, and momentum is just an aberration of how straight the line is of your movement. So if you're going to go slower than the speed of light, it just means that you're rotating or spinning or screwing your way through space, or in some other way you're not going in a straight line, and that would be less than, then you could reduce speed. So there's no momentum. You can move in any direction at any time when you're quanta, when you're the school of fish, you know, it's when, say if you had a school of fish, you can kind of understand that if all the fish decide to go one way, they go that way, no problem. But if it was a school of fish connect to a school of fish, connect to a school of fish, connect to a school of fish, you can sort of understand that one school of fish crashes into the other school of fish, and then it kind of gives it the indication that maybe we want to go that way, but it's not going to go instantly that way because it has to communicate the idea of that way to the other school of fish. And so there's a cascading of this thing, and that's what we call momentum. But that's not the nature of physics. Physics should understand that momentum isn't, you know, it's like they have gravity upside down, where we think about gravity affecting whole pieces of matter when it's just really affecting the atoms and the subatomic particles inside of you. They're the things really being affected by gravity. And we have just the opposite view of momentum, where we think of that as being a fundamental property, and that's really an aberration. That one's really a consequence of much more complex movement. Yeah, I think that was a good enough explanation.
That's it.
Oh, come on, man. Come on, buddy. And now it's going to play the ad. Okay. Bastards. Creepy fuckers. Son of a bitches.
The new Sierra Denali HD features the distinctive Denali grill.
Fuck you, fuck you, fuck you, fuck you, fuck you, fuck you, fuck you.
Was that
Poofed her
according
car.
to the standard particle or standard model of
I already said that.
particles,
If they're going to play an ad, they at least ought to play the ad at the right, you know, put me back at the right place.
There was something seriously wrong with the standard model. So what has happened? They've said this gives us the opportunity to modify the standard model. In other words, please send more money.
Yeah, you can say it's all about research dollars and all this kind of stuff, but it's really about, you know, devotion, tradition. You know, people are, yeah, I don't know what the, you know, but obviously there is a psychological element to this whole thing of where theory migrates, and, you know, how the democracy of intellectuals, or however you want to describe this ivory tower, and what it decides is the right way to go. Yeah, its judgment just isn't good enough. So the powers that be within the community of revered and respected poobahs of physics, yeah, they don't have it right. They're sitting on a frickin' mule. They're not on a horse.
The electron is defined, as I said, as a fundamental indivisible particle.
Yeah, I'm just not sure that there's too many physicists who are doing that now. So I think they understand that electrons are full of stuff. They created this anti-electron, it's, you know, pile of shit. But anyway, and so they have this idea of electron hits electron and it releases quanta. So I think they do know that the electron maybe isn't fundamental. It's certainly not a cannot create or destroy thing. It is a obviously destroyable thing. So the only question would be is whether it's a creatable thing. I mean, I don't think they know how they're created, but they certainly know how they're destroyed.
It goes for all subatomic particles, and this simple repeated atomic model is at a far smaller scale. You remember the ping pong ball in the middle of that ground and the flea on the outside? That means that within those tiny objects there's also spinning charged smaller objects.
Spinning charged smaller objects, that's what I'd say is, you know, there's no charge on those little quanta. The quanta themselves are not charged beyond this idea of polarization. And the machinery of their construction will create the circumstance where it goes in polarization A and it goes out polarization B, kind of a thing. It will create a circumstance where nothing leaves polarized in any direction but one. So it comes in mixed and it comes out one thing.
Who is to say where we stand in the cosmic scale of things?
I don't even know what that means. So, I just mean it's not really appropriate to the conversation. Who cares where we stand? I think it's kind of obvious where we do stand. I mean, we do stand in this idea that the phenomenon starts with, it isn't, as some people think, it isn't completely fractal. Okay, it isn't solid fractal all the way. It isn't turtles all the way down or some kind of thing all the way down. That the physics does change as you change the density of the quanta. So the big universe behaves differently. It doesn't make animals. It doesn't make DNA molecules. This mid-sized space where quanta is only twice as huge or small as it would be in the megaverse, the big universe, the quanta is really small compared to a sun. The quanta compared to our size is a different kind of size, and the quanta compared to an electron is a different kind of size. And those scales, we're somewhere, not in the middle, but somewhere between the extremes of the biggest thing, the black hole, and the smallest thing. Well, I don't know, biggest thing would probably be more like the nebula. And the smallest thing, which is the quanta. So I think we can locate ourselves on the scale map, and we can understand at different scales, different possibilities exist. But different possibilities for arrangement and function. And we just happen to be, quite obviously, in the scale that's the only one capable of creating complex forms, neurons, consciousness.
Now, Ralph Sainsbury, who was the fellow I mentioned earlier,
Not too interesting. Let's read this. The subparticles orbiting within the classical radius of an electron are moving far faster than the speed of light. Now, that's a problem. So, yeah, he's arguing that the things inside the electron are moving faster than the speed of light. From what evidence? They certainly don't leave moving faster than the speed of light. And again, to presume that there is something that can do that is just so dangerous, because you'd automatically, let's just say that there was something that was. The idea that we would have discovered that trick would already exist, because we could send those particles. We can cause the electron of one item to release some of its super fast particles and receive them at some other electron, and instantaneous communication. And there's absolutely no evidence of any such thing. No real hard evidence of any such communication.
this idea of electron structure showed that you could actually derive the magnetic force from this structure. In other words, it's a version of the electric force, and gravity from this structure. It's another weak form of the electric force. So here we are, we're doing what classical physics was designed to do, simplify.
Yeah, but you've simplified based on an idea that doesn't have any mechanical structure. So again, you're not doing anything better than just saying the space is bent. You're saying the particle attracts. And you have no mechanism to defend or define or describe in any simple way how it possibly does that. Where if you just quantize the material and understand that the material itself, the ether, has the energy, that the particles are already moving, and that all matter is doing is changing the arrangement of the movement. It's changing something going in straight line vectors into a practical end result consequence that is going around in circles. Now, it's not literally going around in a circle, but the arrangement of its probabilistic condition is an order, just like a magnet just as two magnets could rigidly hold a thing in a bind of between attraction and repulsion.
Now if they hand out Nobel Prizes for inventing more forces and more particles, and we know less and less the more they do that.
Right, well, I think you're still relying on more than one force, in the sense that you don't have an explanation for this thing you call attraction. You just say, attraction, and that's not a unification of anything. Where, again, I'll just argue, a kinetic particle pressure field, an already moving kinetic particle field without friction, an indivisible quanta, does work. Quantum physics works. You just have to understand what the quanta is.
Ralph Sainsbury, though, said if you calculate the speed of these orbiting little subparticles inside the electron, it's phenomenally faster than the speed of light. He calculated that if those tiny little
Right, because he's calculating it based on assumptions that it's a thing, that it's not made out of quanta, and that you haven't reduced it to its quanta.
Particles were to be released from the electron, they could travel from here to the far side of the Andromeda galaxy in 1 second. This comes back to Newton's law, which doesn't involve time. In other words, it says it's instantaneous. Well, that kind of speed is...
Right, well, we understand that Newton didn't have any capacity to make those kind of time calculations. Well, you might have... He just didn't have the... Newton did everything, so the fact that he didn't figure out that maybe he could test for the speed of gravity, you're not going to take points off of that, or for the speed of light. So I just think, that's sort of a cheap shot at Newton. And Newton didn't really believe in instantaneous based on evidence. He just believed in it because there was no reason to believe in anything else. It's so fast to perception that you think light is immediate. And it isn't until somebody tells you it's not instantaneous that you can know it's not instantaneous. It's not obvious to the experiment we do with our senses. Our senses see light as being pretty fucking instantaneous. It's just a wrong perception.
Instantaneous on our scale and on a galactic scale. Tom Van Flandern did his own astronomical calculations to point out that the Earth orbits the Sun and it knows where the Sun is right now. And it's fairly easy to determine that. And
okay, says him. I would argue that that is not happening. There's no evidence of any instantaneous connection, and if there were, we could create gravity devices or some other device to instantaneously communicate, and no such thing is possible.
By using a more stringent test, he calculated that the speed of gravity exceeded 20 billion times the speed of light.
These are theoretical tests, I'm sure, so I don't think they have any value.
So the difference between that and Ralph Sainsbury's was about the order of 1,000 times. Ralph Sainsbury's is probably more accurate.
So right there, he's basically making an argument for this instantaneous communication that I don't think advances his theory any, and I don't think is necessary to his theory. It's just some way of setting it apart from the standard, the known standard. But I'm just saying I don't think there's anything necessarily wrong with the known standard of recognizing that light travels at a certain speed, depending on the medium. And in the vacuum of space, the medium is retarding enough to keep it to 365,000 miles a second, where through some other medium it might be a different speed. But again, speed is calculated by distance, which is always tricky because light doesn't necessarily travel a straight line when it's going through a medium.
So the electric force between matter, particles, must operate instantly on our scale of things for the electron to be stable.
I'm just saying that you see that that's a conclusion based on a conclusion. So that's not worth much. I mean, a conclusion based, there's no evidence in that circle of conclusion leads to conclusion. Well, unfortunately, you don't have enough evidence to justify the first conclusion, so the second conclusion is just as bad as the first.
But something comes out of this is that once you have the speed of information exchange almost infinite, then time is universal. Time has nothing to do with Einstein's clocks.
Well, this is again, this is accurate to say that relativity is a nice metaphor, but it's just the wrong story. This isn't the Goldilocks story. This is the Three Pigs story, and it's just the wrong way to describe what the reality is. The fact is that matter can be slowed down, can be retarded, not time itself. So stuff, when it's got velocity, will start to function slower. That's all. It's an absolute fact. It has nothing to do with anything relative, and it has nothing to do with space. It just has to do with your condition. If you're moving very, very fast, your matter is going to be functioning very, very slow.
The physical things, they're made up of atoms and so on, and their environment can change the way they tick. So to use the clock...
So again, it's not their environment that changes how they tick. It's their condition, what they are doing. You're moving at 3/4 the speed of light, your metabolism is slowing down.
There's a surrogate for the concept of time was completely inadmissible. So Einstein's special theory of relativity, I'm afraid, is discounted immediately.
Well, both theories of relativity are useless as descriptions of reality, and they're only useful in this context that to perception, it's always going to be a relative comparison. You're comparing your condition to something else's condition to something else's condition, and they're all going to be relativistic conditions in the sense that you don't know what the 0 point is. You're just comparing. I'm 10 feet high, he's 20 feet high, he's 5 feet high. So you're just going by whether something's higher or lower, but you don't know where you are on a scale to start with.
So, Newton was right. Gravity is effectively instantaneous.
Well, again, it wasn't Newton. Newton did not make that conclusion based on any evidence except perception. So he was not making, that wasn't part of his theory. That wasn't part of his, wow, I've observed the universe and this is my conclusion about what the truth is. He was just guessing because he didn't have any other reason to guess anything else. He had no reason to suspect it was slower than instantaneous, so he didn't assume it was slower than instantaneous. But quite obviously, we understand that it is.
And Einstein strayed from the path to discovery by postulating the speed of light as the maximum speed for information transfer. When he did that, he disconnected everything.
Well, I mean, he didn't even do that. The evidence did that. But again, because there's no evidence of information being transferred at anything faster than the speed of light. So, I mean, there's just no evidence in the universe. There's no mechanism that can do that. And if there was such a mechanism, we would have used it. It would be very nice if we could have communicated with our probes that are in space instantaneously, and we didn't have to wait for radio waves to get there.
He made an unworkable universe. To have a workable universe, all of the components of the universe must know what all the other components are doing.
Yeah, well, that's true. That conservation exists, but it exists in a time envelope. The knowledge takes time, and that's part of the reason why the whole universe does work, in a sense, is that delay is part of the function. It's part of the error. It's part of the... It's part of the mechanism that allows for induction and allows for fields to be created and destroyed. Ironically, you know, the Teslaites, you know, in a sense, alternating current might not work in an instantaneous. If fields were created instantaneously, alternating current might not even work. It is the idea of the field building and the field collapsing that provides the opportunity for there to be work value in alternating current.
In real time. The difference between this idea and Einstein's is rather like you drop a a pebble into a pond and you pick up the sound wave, which is a compressional direct wave, it's much faster than
well, it's much faster, but it's still a hell of a lot slower than instantaneous, so what's the argument? Sound is different than tension waves across the what do you call that one? The attraction between the molecules of water. Oh, frick. But anyway, those waves, you know, the more viscous the substance, the less viscous will decide how fast waves on the surface travel. That's a completely different science than sound waves traveling through the thick medium versus a thin atmospheric medium versus some other medium. Sound is not a surface wave. Sound is a vibrational wave. They're two different things. One's decided by tension and density of the medium you're waving, changing its, you're oscillating its pressure, its internal buoyancy, and the other one is a vibration traveling through. So they're two different things. Very different things. So why would this is not a fair comparison. Sound isn't magic. It's just a different form of communicated force.
Ripple itself, which takes time. Light is a ripple. It takes time to pass through the...
So again, it's, you know, obviously by my theory, it's not a ripple, it's a period. It's a quanta, space, quanta, space, quanta, space, quanta. But there's no ripple, there's no wave, there's none of that crap. The frequency is just a definition of the time interval between the quanta, the elemental particles. So a photon you see, to see you have to see the period, you have to see at least two, technically two photons. It's not one, it's two quanta make a photon, so to speak. Not mathematically. Mathematically you could still count them as a half a photon would still be a photon, and three quanta would be, you know, it would, we would call it probably a photon rather than recognizing the extra half. You see, that kind of thing. So when you detect the mass of a photon, what you really have to do is understand that it's made of quanta, and you have to understand that it can have an odd or an even number of quanta.
Ether, the medium, to the receiver. That's enough of that. With the real meaning for mass, we can attempt to give real meaning to energy as represented by the equation that everyone has seen but no one understands. Energy is charged matter in motion relative to the charged matter in the rest of the universe. That's the first physical definition I think you'll ever see.
Yeah, well, you apply the word charge and it's just totally unnecessary. So if you use the word energy as a recognition of difference in condition, I guess that's sort of the definition of when we see energy, is because there's some circumstance where one thing is going, something here is going there, or, yeah, that's pretty much it. Something's moving. Some piece of matter is moving. We call that energy. And that we understand that the matter is made out of energy, that matter is that movement. The stuff inside the atom has a bunch of movement in it. And at any moment you can release that movement. There are little bits inside of the atom that are moving. Those little bits are its mass, and if you release them, there's a certain amount of movement that they represent, and it's consistent. So if you have an atom with an atomic weight of 15, you know, there's 15 million of those things. And if you have an atomic weight of 30, then there's 30 million. That's all.
If you look up encyclopedias and textbooks, they give examples and how one changes from one form to another. But they don't actually explain at a fundamental level what it is.
Well, I think the idea, quantum mechanics, I think that terminology was on the right course. That terminology was basically saying there's a quantizable element to this thing called energy, a notion of energy, and that would be this quantum moving one quantum distance in a quantum amount of time, a Planck, the most elemental function. Reduced to its most elemental function, there's a oneness. There's the oneness of the amount, the quanta, a oneness of the amount of speed, the speed of light, a oneness amount of distance that you travel in a oneness amount of time. That's it. And that was the right course. They just fell off the wagon when they started doing this kind of thing, paying attention to waves, which are consequences, not fundamental. Waves are not elemental function. Waves are consequential function.
That's the one. Electromagnetic.
Okay, energy is changed matter in motion relative to a changed matter in the rest of the universe. So that's a kind of a good statement. Energy is a changed matter. Energy is changed matter in motion relative to the changed matter in the rest of the universe. So that's back where I want to get to this conservation argument again. So again, if I lose something, you know, if something going this way and I let go something going that way, the field, the universe, now gained an extra one of these. And so if you just think of them as red, blue, and green, and I've collected in matter 30 reds and 40 greens and 30 blues, then there's 10 less greens in the field, right? Was it greens I had 40 of? Well, whatever the difference is. The field is absent the extra I took, or the field has an excess of the stuff I have less of. That kind of argument. So wherever imbalance is in matter, the reciprocal balance exists in the field. The field wants to put it back in balance. It'll tend to try. Okay, electromagnetic energy is stored in the resonant orbital structure of the subatomic particles and manifest as their mass. So the resonant orbital structure is really just a straight line structure converted to an orbit. So it's really nothing more than exactly what the Earth is doing around the Sun, and that simple mechanic is that something that was going straight at a velocity is now going in a circle at a velocity, and at any point if you release it from its gravitational bond, it goes back to being what we would call energy. So it's not energy when it's circling the Sun, it is energy when you let go. But it's the same thing, and all you're going to do is change what direction it leaves in. It came in one direction, it can leave in any direction, depending on when you turn the gravity on and off.
Energy is stored in the resonant orbital structure of all subatomic particles. It's matter in motion. And the mass of a particle is a measure of how much energy is absorbed internally, and its deformation rather than its acceleration. It's rather like having a balloon.
See, it just has nothing to do with its deformation or its acceleration. Its mass is just like the solar system. The solar system has a mass. It just doesn't matter where Pluto is and where Venus is or how fast they're going or any of that other kind of crap. It doesn't really mean a damn thing. What it is what it is. How fast they're going does matter, obviously. But I'm just saying, in the quantum world, again, there is no different size and different speed. There's only one size quanta, and it's all the same, BB, and they're all going the same speed.
Full of water, and you poke it, it resists moving and deforms instead. Well, these particles do the same.
No, they don't. So that's just wrong.
And this is
I mean, deform in the same sense is where they have some elasticity and some automatic capacity to bounce back. There's nothing automatic necessarily. There's nothing elastic. There's nothing. They're quite breakable. They're more like crystals. And you can force them to break and reform, but you can't really bend them.
What was his name again? The chap earlier who I mentioned, he said that we had to look at the electrical, or the idea that when you put electrical energy into a particle, like in a particle accelerator, the mass of that particle seems to change. It's that concept that you really had to focus on.
Yeah, well, particle accelerators are a very unnatural condition, quite obviously, and any measurement of its mass would be a measurement, certainly, of the idea that it's collecting probably some of the energy you're throwing at it to move it. So you're imposing on it a huge amount of quanta moving in a direction to get it to move in a direction. So you keep creating a field of energetic particles hitting at quanta and pushing it. And the idea is that some of what you're going to receive at the target is just going to be residual energy from your pushing. You're just going to, some of your footprint is going with the thing your foot is pushing. You know, so you're not going to get just the bubble gum, you're going to get some of the foot.
So what causes gravity? The gravitational mass equals the inertial mass. That's the lifting and pushing. So much.
Okay, the gravitational mass equals the inertial mass. No. I mean, that, you know, it just, there's no point in talking about it. The gravity exists no matter what speed. So speed isn't going to change your gravity. And so it just, inertia doesn't have much to do with gravity.
The same mechanism is responsible for gravity. Now, atomic electrostatic dipoles, as I've talked about with the London force and so on, are formed...
So again, this is unnecessarily complex language. Atomic electrostatic dipoles is just basically saying the establishment of a plus and a minus, a polarized atom.
By most atoms inside the Earth, with the inner pole positive and the outer pole negative. The reason is that gravity is pulling on the nucleus. You can't shield gravity. That's the point. So the fact that the electron's down there doesn't matter so much, except that it holds the nucleus back from moving in the gravitational field. The nucleus is...
Well, like I said, it can't really hold it back, but the point is that over a period of time, this atom could be in many shapes, but the predominance, the net effect of all those shapes will be this shape. So over a 10-second period or whatever the amount of time you want to do it, this is what it's going to look like. Just like any probabilistic pattern of rolling dice or flipping cards, the cards can have they can fluctuate with each permutation, but in the end you're going to get a pattern. And the fact is this will be the pattern you'll have if you add up all the directions and all the shapes and all the sizes, and you average them. This will be what you'll end up with.
About 1,800 times heavier than the electron. So if it moves in the direction that gravity is pulling it, then the atom is distorted, as I've shown there. Which means...
Right, but it's, like I said, you know, it's distorted in the sense that it, in a net condition, that's the condition. But there will be periods or moments, what do they call that, the magnetic moment or whatever, where it's not in that condition. But they'll be brief, you know, because most of the condition is going to be consistent with what you're seeing as its effect. But the cause is more complicated. The cause has moments where it doesn't look anything like that.
That the bottom end of that atom is more positive than the end nearest the surface, which is more negative. Simply because the electron spends more time out at the top of the curve. And
so you know, another part of this is a little bit bogus, is they should just put this minus sign down here, just to recognize that this actually should be the minus, and this should be the plus here, just indicating that this is your dipole. This is creating your polarized condition, is the fact that this positive is exposed to this surface, and the negative down here is predominantly in that direction, so that your net effect is that this is now this whole entity becomes a charged atom. So an uncharged atom is one, a neutral atom is one where their balance is perfect on all sides, and so no matter where you look at it from, it's always got a balance between how often this shape, the minus would be swinging in front, and so it's always flashing on and off equally. So it's positive and negative in an equal amount, and this would be more like a velocity. An atom that has velocity would have this misshape that'll tend polarize the matter. And this would certainly be the shape of some magnetic element. The atoms would have that condition where all the pluses and the minuses line up in the same direction.
Short amount of time at the bottom. So, the electric field produced within the atom distorts the subatomic particles. So, the particles within the atom, the nucleus, and the electron are all distorted similarly by a very tiny amount. And this is the distinction between the gravitational force and the electric force. The amount of distortion is infinitesimal. 10 to the minus 38, 10 to the minus 39 times the gravitational force.
Well, again, I would argue that there's no other force but the gravitational force, and all you're doing is describing how the force is changed and what kind of proportions the change is once you polarize the gravity. Once you have polarized quanta, the change becomes significant in the sense that the gravity becomes ineffective or completely effective. The capacity for it to create effect is I mean, you could argue 2 times, but that's 2 times 1 quanta effect. So it's still, you know, no point in trying to calculate because it's 0 from 1. So times 0 doesn't work anyway.
So, it is the sum of all of the aligned subatomic dipoles that produces the profoundly weak force of gravity.
Well, I just think that's nonsense. Gravity isn't dependent on any of these dipoles existing. So gravity has nothing to do with dipoles. It just has to do with the existence of atoms and the fact that they have an atomic weight. And their atomic weight isn't based on dipolarization. Their atomic weight is based on the existence of the little bits inside of the atom.
And the fact that they're held by the molecular forces, which is far stronger.
See, he's making up another force now, the molecular forces, which are far stronger. So now we have another force of attraction or bond or association, and far stronger, blah, blah, blah. Yeah, I just don't see any point in that rhetoric. It's all the same force. Everything gets pushed together. And when something's being repulsed, that's really just a way of saying it's being pushed away. You know, there's more push in between us than there is pull, because the stuff that was hitting me from behind and having an effect isn't having well, it's the opposite. The stuff in front of me has twice as much force as it has if it's not polarized. So if I'm sensitive to the thing that's coming out, and the thing that's coming out is all in the direction of the stuff I'm sensitive to, then the pressure here is going to be greater than the pressure behind me, even though there's not the same number of quanta. So even though it's less quanta, it'll be hitting me, they're twice as effective. So that would be the argument. So obviously, if they're twice as effective, I only need half as much